Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the last lecture of this week and today's topic is analysis of plane frame computer implementation. You see, we have in this week we already have a detailed discussion on various steps involved in finite element method, and for a better comprehension we had done manual calculation for truss problem, manual calculation for beam problem, to understand, to comprehend those steps in a better way. We will not repeat those things today. The steps will be exactly same. Here what we'll do is we'll just take one example, straight away go to the computer program and get the results from there, and then we'll increase the number of elements and then see what happens to the solution. Okay. Now, so this is the brief review of what we know about frame element. This is essentially the combination of truss and beam. So this give you the stiffness matrix, and again red color 1 and 2 are the degrees with the node number. This element is connected between node number 1 and 2, and 1, 2, 3, 4, 5, 6 are the degrees of freedom. And then element level equation is this, where K bar is the element stiffness matrix, U bar is the element level degrees of freedom, and Fe bar is the element level force vector. And then but then we can have different member in different orientation. These expressions, these stiffness matrix and these equations are written with respect to the global coordinate system, but then all these equations of all the elements need to be represented with respect to a global coordinate system, and that can be done through a transformation. And this is the transformation matrix, and this transformation matrix depends on the orientation alpha, and this is the alpha. This is alpha. And then once we have this transformation matrix, this is the relation between the element level degrees of freedom and the global representation of the degrees of freedom. This is for the force vector, and the stiffness matrix can be obtained. The element stiffness matrix can be obtained. Element stiffness matrix with respect to the global coordinate system. Ke bar is the element stiffness matrix with respect to the local coordinate system. Now the global coordinate system can be obtained by this, and this is the element level equation written with respect to the global coordinate system, whereas this one is the element level equation written with respect to the local coordinate system. So first we have to translate we have to represent all these your force vector, displacement vector, and then stiffness matrices for all elements with respect to the global coordinate system, and then assemble them. Right. Now let us take one example. Now let's take two node. We have one node here, we have another node here, and we have another node here. So this is element number 1 and then element number 2. Okay, this is node number 1, this is node number 2, and this is node number 3. And this coordinates are, this coordinate is 4, 4, and this coordinate is 0, 4, and this coordinate is 0, 0. Okay, and then force we have here is 10 kilonewton load. Now let's go to the program now. So this is the program for analyzing plane frame using finite element method. So the same thing, first you have to give the nodal coordinate, and then second is the element connectivity. For this problem it is connected between node number 1, 2, and then second element is connected between node number 2, 3, and this gives you the total number of node we have in the system, total number of element we have in the system, and total number of degrees of freedom. Now there is a difference here. In case of class problem, we had 2 degrees of freedom at every node, so total degrees of freedom was 2 into the number of node. In case of beam problem also, there were 2 degrees of freedom at each node, but here we have 3 degrees of freedom, so this is 3 into this. Now these are the area, Young's modulus area and second moment of area we require. We can give some values here. Now this is the boundary conditions. What is the boundary conditions we have at the element number 1? So at the element number 1, all degrees of freedom are constant. What are the degrees of freedom we have at element number 1? We have this, we have this, and then this, and then this. So this is 1, this is 2, and this is 3. So at element number 1, all are 0, right? This is how we are defining our boundary condition. So this is the boundary condition. Now this is the Q axial, the load we have. In this problem we do not have any distributed load, only we have a concentrated load here at element number 3. So the direction at element number 3, the force will be element number 3, this direction there is no force, 0, and then this direction it is -10, and there is no moment, so it is 0. So this will be the Q for us. Okay. Now this is the Q. Now this the input, and the rest of the code is very similar to the code we already had, the program we already had for Strass and Frem. So this is the globalization of the initialization of the global displacement vector. This is the initialization of the global stiffness matrix, and this is the initialization of the global load vector, and then in the global load vector is populated with the information about Q we have. These are the boundary condition. This identifies the boundaries where the conditions are prescribed, constraints are prescribed, and it identifies the boundaries where the constraints are not prescribed. Now this is the initialization of partition matrices, and next is the computation of global stiffness matrix. So this is I1 and J1 at the element E is connected between node number I1 and J1. I1 is the first point and J1 is the second point, and H is the length of the element, and mu is this. If we see the elements in the matrix, mu is A square by 2i. This is mu. Actually this part, the first row and the third row, and first column and the third column correspond to the axial deformation, right? So this is mu. Now we need to calculate sine theta and cos theta. So this gives you sine theta and cos theta. This is the transformation matrix. Now and then once we have the transformation matrix, this Ke is the element stiffness matrix written with respect to the element coordinate system, and then we have to find out the global element stiffness matrix with respect to the global coordinate system like this. Okay. Now then this is the then we can assemble them depending on the connectivity, and this vector identifies the connectivity or identifies the degrees of freedom of that particular element. So this gives you the global stiffness, global load vector. Once we have the global load vector, then the next is the partitioning of the we have to solve it, then we have to partition it, we have to get the condensed equations. So this does this. And then finally solution. The solution is exactly the same. This is the solution. Once we know the unknown displacement, then we need to find out the unknown forces, which are the reactions here. So we can find out unknown forces and then populate the global degrees of freedom, the vector we have, update it based on the computed displacement. Now this is the plotting of this entire frame, the undeformed coordinate and deformed coordinate. This xy gives you the undeformed configuration, and x1 and y1, which is essentially the undeformed configuration plus the a node 1 is the undeformed configuration plus the deformation gives you the deformed configuration. Then you plot it. Okay. Now if you plot it, then our results will be something like this. Okay, and if we check the result, what are the results we have? U will be U, or let's plot the global vector. So U will be this. So first these three are at this point, these are 0, and these next three are at this point, the second point. This is this is horizontal, this is vertical, and this is rotation, and this is the third point, means the point where the load is being applied. So this is the result. Let's see the reactions. So reactions will be at this horizontal reaction is 0, this is 0, and the vertical reaction will be 10, which is downward we have 10 kilonewton force, vertical direction also 10, and the moment will be 40. 10 multiplied by this length is 4, so 40. So this is consistent with the solution. Now this is the solution we obtained from just 2 elements. Okay, now let us increase the number of elements and then check what happens to this solution. Now this is the here is the same code, but now we have total 8 elements. For each member is divided further into 8 elements, and then and the rest of the thing are same. Then if we now in this case, please note it is at external force when we have to apply. It is now at element number 9, node number 9. The force need to be applied. Now if we run it, and this is the deformation, and if we see the element U, this is the last one. If you compare, you can compare all, but the last one, this point, and this point are the common in the sense the previous discretization and this discretization, and we can see that at the nodal point these values are same. The same value that we obtained from just one element for one member discretization. Now next we will not do that step here. Next we need to see what happens once we obtain the values at the nodal point. What happens within the element? We know how to approximate, how to compute the deformation within the element. We know how to compute the member forces, bending moment or actual force within the element. We can apply the same approach to find out those values, deformation and the forces within the element, and then compare those values with the value we can obtain from the strength of material approach, right? So that exercise will be same. We have already done that exercise in case of beam, so same exercise can be done here. So we will not do that here. Now, so this is the implementation of finite element method for a truss problem, and then beam problem, and then this is frame problem. I repeat once again what I said in the last class. Eventually we will see that when you are in industry, you will be using some commercial software or some software developed in the industry for the kind of problem that particular industry deals with. But to understand various steps in finite element method, to have a better appreciation of finite element method, better comprehension of the finite element method, it is very, very important you write a small program at least once. Okay, this is very important. Only knowing the theory is extremely important, but only knowing the theory is incomplete until and unless you translate that theory into this small program for implementation. Now, so you see that more or less the codes are almost the programs are almost the same for the problem, but only thing is the input need to be given separately. Now you see, even if you use some commercial software, only does these operations, this solution part, right? It is we who have to create the model. It is we who have to give the discretize the structure, give the boundary conditions, give the loading, give all the properties, right? It is we have who have to decide which idealization to be taken for the solution. So what input we give in the solution, in the method, that is extremely important. Okay, so that need to be consistent with the problem that we are dealing with. So there is a term called GIGO, which the meaning is garbage in, garbage out. Means, you see, finite element as a method, it will, whatever values you give, it will solve, it will give you some result, right? But then what values you are giving, what kind of elements you are using, those things need to be consistent with the problem that we are dealing with. That is extremely important. Okay, so with this note, let us conclude this week. Next week we will discuss finite element formulation for two-dimensional problem. Thank you. See you in the next week.